So here is a pretty practical question. Let's say we have a sequence where we start off with some number r, and then we look at r squared, and then we look at r cubed, and then we look at r to the fourth, right? That's a sequence. Does that converge or not? This is exactly the same thing I was looking at in my graph. My value of r was 1/2. So whether or not this converges will depend on what number we start out with. So if I pick a number that is greater than 1, then r, maybe it's 2, maybe it's 3, maybe it's 1,000,000. When I square that number, I'll get something bigger. When I cube that number, I'll get something bigger again. When I take that number to the fourth power, I'll get something bigger still. And so in the limit, that will diverge. That limit will go to infinity. Now, if I pick a number between 0 and 1, then I know in the limit, say I take 1/2, then I square it, I get 1/4. I cube 1/2, I get 1/8, and so on. We've already seen that that will tend towards 0, and the limit will exist. And what's going on here is I'm just using the intuition from studying functions that look like a to the power x. Again, this is something that we could have done in Calculus 1, looking at some real number x as x goes to infinity. And just to tie off the last bits of this problem, if I have 1 to the power n, I know that 1 to any power is itself, so the limit is just going to be 1. If I'm taking the limit of 0 to the power n, the very same reasoning holds. 0 to any power is itself, so I just get 0 as the limiting value of the sequence. So each of these are constant sequences, even though their formula does have an n in them, and their limit will just be 1 and 0, respectively. Now, I'm not quite done here, because I could have a negative value of r. So maybe r is between the numbers -1 and 0. Well, then I can just use my squeeze theorem argument, right? So I can just look at the absolute value of r to the n instead. I know that the absolute value of something raised to a power is equal to the absolute value of the number r, which is then raised to the power n. And I already know that this limit is going to be 0, since I have a positive number raised to the power n. I'm taking n going to infinity, and I know that my positive number is between 0 and 1. And then the last thing to check is if r is negative, well then for the very same reason that I saw on the previous slide, say I have a negative number like -6. If I square it, I'll get something positive, but it will be larger in magnitude. If I cube that number, I'll get something negative again, and it will be larger again in magnitude, right, in its absolute value. And so that limit will, again, diverge. There's no real number that sequence will be clustering around. So here are some pictures to illustrate what's going on. So if r equals -1, we just flip-flop back between -1 and +1. That doesn't cluster anywhere, so that does not have a limit. For r between 0 and +1, we see this kind of behavior here in this lower left graph. In fact, this has all of the positive cases. So in blue here, r greater than 1 will diverge. They'll go to positive infinity. R between 0 and 1 will converge. They will tend towards the x-axis here. They'll go to 0. R equals 1 is my nice constant sequence. And then here are my negative cases. For r between -1 and 0, I get this alternating behavior, but it still converges to 0. For r less than -1, I get this alternating behavior where every time I go, the magnitude of that number grows.